Hello and welcome to this tutorial. In today's video tutorial, I'm going to walk you through an end-to-end deep learning pipeline for extracting building footprints from aerial imagery using a pre-trained unit with a ResNet encoder. So we are going to do all this in Colab as usual. So I'm going to show you how to post-process and regularize the outputs for a cleaner building polygons. Okay, so why are we doing this? Remember in the previous videos, we noted that our boundary IoU was very low, around 38%. So we want to improve the boundary IoU. Right, so we start by installing and importing the necessary libraries. So here we are going to install these libraries which are not available here. So, for example, segmentation modules from PyTorch. And after that, we are going to import the required libraries. Some of the libraries I explained in the previous video tutorials, so I'm not going to detail. And then next, we are going to mount a Google Drive. And remember, this is where our datasets are located. So for my case, they're located in this working directory. So next, we are going to load the area orthophoto image here and the corresponding building footprint polygon, which is saved as GeoJSON file. So we are using ResNet34 and GeoPandas to import these datasets. Right. We are also going to rasterize the building polygons so that it's ready to be used as a binary mask with buildings as 1 and the background as 0. Okay, so next, to train a segmentation model, we are going to break the large image. Remember that area photo and mask into 256 by 256 pixel patches. So here we are going to define a custom dataset class in PyTorch so that we can efficiently load these patches for training and testing. So here we are going to also split next the dataset into 80% that is going to use for training and 20% that is going to be used for testing. And the batch size here is 4. Right, now we come to the model. So here, as we said, we are just using a pre-trained model. So this is transfer learning. So we are going to use a unit architecture and with ResNet34 encoder. So this is pre-trained on ImageNet. Okay, so this is going to give us a very good starting point so that the model can learn faster with fewer labeled examples. Okay, so we are going to initialize the unit model using the segmentation models or Python. So SMP means segmentation models Python. So this is a library which provides access to the state-of-the-art segmentation architecture with pre-trained encoders. Right, so before we doing that, we have to check whether we are using a GPU or if whether GPU or a CPU is available. So in this case, I'm using GPU. So make sure that here you change your runtime here to GPU. Right. So before we go further, let's talk about ResNet. So what is a ResNet 34 encoder? So a ResNet 34 encoder refers to the use of ResNet 34 model, which is part of the encoder of the neural network. So ResNet34 is a 34-layer deep convolutional neural network from the residual network family, which was introduced by Microsoft Research in 2015. So remember, the encoder is part of that network that extracts the hierarchical features from the input data. Right. So here we have, as I said, we're using the ResNet34, and the encoder weights, they are coming from ImageNet. Okay. So ImageNet here is a massive labeled dataset for training deep learning models. So it has got about 14 million labeled images. So it's a massive dataset. Okay, so simply here we are saying that we are going to initialize the encoder with the weights pre-trained on this ImageNet. So this is going to improve performance through transfer learning. Right, and our channels, we have got an image with 3 channels, red, blue, and green, and we simply are going to have, we're extracting the building footprint, so which is just one class. So if you run this code, it's actually fast, it is very fast, maybe it takes 2 or 3 minutes. Right, so this is transfer learning. So it's faster than the previous models that we have created in the previous videos, because in the previous videos we are training from the start, but here we are just using a transfer model. Right. So next, following that, we are going just to use a binary cross entropy with logits and the Adam optimizer. And then next we are just going to train the model for 10 epochs. And then we will be tracking the training and validation. Okay, and we are also going to track the training accuracy and the validation accuracy. So this is going to give us the performance of the models. So in other words, this gives us a good sense of whether we are overfitting or we are improving steadily as we proceed with the training. Right, so these are some of the training outcomes. As you can see, model is doing quite well. Right, next we are going to plot the model performance over time. So again, this gives us a good sense of whether we are also doing well or whether we are not overfitting. So this is the final graph that we have. So we have here the training loss and the validation loss. As you can see, training loss is decreasing, and sometimes it goes up, and then here also the validation loss going up and then going down. But in general, the difference between the training loss and validation loss is not very high. So we're not having an issue with overfitting here. And same for the accuracy. So accuracy is going up steadily, although there are some fluctuations. And same for the test accuracy here, which is also going up. Right. So once the model is trained, now we can use it to predict the building footprint mask across the image. So here we're just going to do the tiling and stitching the patches together. And following that, we evaluate the performance using the common metrics, that is the F1 score and the intersection over union. We also are going to use the dice coefficient, and finally we want to check the boundary IoU. Right, so this is the results from the model. You can see that we have a very high F1 score. The IoU also is very high, and the dice coefficient is very high, and we have an improvement in the boundary IoU. So from 38 in the previous unit model to about to 53 to 53%. So from 38% to 53%. So this is quite good news, right? And then next we can display the predicted masks, and then we can also compare with the ground truth data. So this is the original input image, the ortho image, and then these are the reference or ground truth mask, and then this is the predicted. And as you can see, the model is actually trying to is doing a good job in predicting, although we can see some misses here and there, but generally this is quite good. Right, so following that, we can now convert the polygons, and then we can convert the predicted mask to polygons, and then we can save them as a GeoJSON file. And I also want to clean up the polygons a bit. So here we perform regularization, and then we can save the regularized building polygons in GeoJSON again, and then we can later access them in Google Drive. Right, just for interest sake, we can also save the trained model. Sorry for this one. So we can save the trained model so that we can reuse it later if we want to do other kind of fine-tuning, or we want to train it with other data sets, or we want to use it for inference purposes. Alright, so that is all about this tutorial. So you've seen how you can use the pre-trained unit model through transfer learning. So this is actually faster than actually creating your own model from scratch. Right, so we will continue working on some of these pre-trained models as we move on with our tutorials. So thank you very much for watching this video tutorial. See you in the next one.